Okay, so we're going to start today looking at how fundamental theorem of calculus is going to relate to definite integrals, because we have looked at infinite integration where we integrated and put the plus c on the end, which technically I would not do until after this section if I had not been doing things out of order, because I was trying to leave easy stuff for you. But we have looked at what it looks like to integrate from like an infinite perspective, but we have not figured out how to take an integral from 7 to 15, right, from a specific point. Which we need to learn. The other day I was doing linear versus exponential growth in my Math 1 class, and I just could not help myself because we were looking at like one person got like $1,000 raise a year and the other person got a 1.5% raise per year, and so like we needed to know which one was going to make more money, and so you have to have calculus to know, like, over their lifetime, like over 30 years of work, and who would make more money. So it was, I had to show them. And then they were saying that you guys needed to do the problem, but we don't quite know what we need to know to do it yet. But in a week or so we will. So it's kind of a cool problem. So the graph v of t is shown to the left. It shows the velocity of a car in feet per second traveling along a straight highway. Find the integral from 0 to 7 of v of t dt and describe, I don't think that should say describe it, and describe its meaning. That doesn't need to have both words there. Describe. All right, so when we're talking about an integral, we are looking at area under the curve, right, or between the curve and the x-axis, or I'm calling it the curve, but in this case it's not really much of a curve, right? So we're looking at between 0 and 7, we're looking at this area right here. And so right now, you guys know how to find that area because that is just a parallelogram, a trapezoid, right? So how do I find the area of a trapezoid? 1/2 height base 1 plus base 2. Yeah, area of a trapezoid. That's one you want to have memorized for sure because you will need it. Another way to think about it is like it's the average of the bases times the height. Because, like, if you add these bases together and divide by 2, that gives you the average of these bases, and then you multiply it by the height. So, the integral from 0 to 7 of v of t dt would equal 1/2. The height of that trapezoid is 2. The bottom base is 7. The top base is 2. So that is going to give us 9 whenever we evaluate that. So our x-axis here is seconds. This is feet per second. When we integrate that, what are our units going to be? It's just position. Because when we take the derivative, we would get feet per second per second. So if we were looking at the slope, we would divide change in y over change in x. If we're finding area, we're multiplying feet per second times seconds, which is like seconds over 1. Seconds will cancel each other, and we'll just get feet. So this is 9 feet. So this is not position. It's going to be how far they've traveled over that time interval. So it's our change in position. Okay, so there's a difference there in position and change in position. So we would say from t equals 0 seconds to t equals 7 seconds, the car moves 9 feet to the right. Or it doesn't specifically tell us positive direction, I guess. We're going to say right. Whatever your positive direction is. Because it's positive, yeah. So what we're looking at here, this is our displacement. It's how far it's traveled in that time interval. Now, it might have started at 15. So if it started at 15, our position would not be 9. Our position would be 15 plus the 9 that it's traveled, right? So we can't call it position. We can call it displacement. We can tell it's how far it moved in that time interval there, but it's not necessarily our position. So let's go to the next part. I thought I changed this. On your paper, does it say 9 to 18? Okay, it should say it should not say 9 to 18. I thought I fixed that. I must not have saved it whenever I did it. So yours should say 7 to 10 v of t dt, and then it should say here 0 to 10 v of t dt. Okay, so from 7 to 10, we are looking at this area, right? Okay. Once again, it is a trapezoid, or, I mean, you can make triangles and rectangles out of it if you want. So our integral from 7 to 10 v of t dt is going to be 1/2 times our height, which is 4, times base 1, which is 3, plus base 2, which is 1. And so that is going to give us 2 times 4, which will give us 8. But it's not just going to be 8. What will I get? It's going to be negative because it's below the x-axis. So the area of that region is 8, but because that area is below the x-axis, the value of this integral is negative. Okay? So this is also going to be feet because this is seconds, this is feet per second. And when we find the area, we're doing feet per second times seconds, which will give us feet. So this would be from 7 to 10 seconds, the car moves 8 feet to the left. Okay, because we have that negative value here, that means our displacement is going to be in a negative direction, which we're calling left here. Yes, yeah. And also when I made this problem, obviously we're like pushing this car or something because it's only going 8 feet in 3 seconds there. So using the two things we have already learned, right, and properties of exponents, 3 asked me for the integral from 0 to 10 of v of t dt, which I could break into 2 pieces, right? I could break it into the first part that I've already done, v of t dt from 0 to 7, plus the integral from 7 to 10 of v of t dt. And so that would be, I got positive 9 for example 1. I got negative 8 for example 2. And so I get 1. So, what does this mean? Okay, I mostly agree with that. Did it just move, like, that's all that it did? It moved 1 foot to the right. It actually moved 9 feet to the right and then back 8 feet to the left, right? So I probably wouldn't phrase it exactly like you have said because it could be interpreted as it only moved 1 foot to the right. So this is where I would it's really good to just use the word displacement because the distance, what's happening here is its distance from its starting point to where it's at the end of 10 seconds is 1 foot. That's its displacement. That's how far it is from where it started. Is that the same as the total distance that this car traveled? It is not. What's the total distance that this car traveled? 17, right? Because if we're talking about the total distance it's traveled, we don't care which direction it's going. It would be all positive. We will also always want to start with the time period that it's happening. So that's 0 to 10. So from 0 to 10 seconds, the car is displaced 1 foot to the right of its original position at t equals 0 seconds. So it's 1 foot to the right of where it started. There. You don't necessarily have to use the word displacement, but you want that idea of like its distance from where the starting point was there. I would be careful with origin because origin kind of like mathematically would indicate that its original position was 0, and we don't know for sure that was the case. It could have started off at like what we would call 5 feet. So I would be careful with that word just because of its mathematical meaning that they might take as another context. So you could just say of its position at t equals 0. You don't have to put original there. There may be some ways you could word it with origin where it would be okay, but I'd be careful because it might not. They might take you saying origin to mean that it's like 0, 0 on the graph, and it might not be. So like if we knew the car started at 7, then after 10 seconds it would be at 8 feet. Whereas if it started at the origin, if it started at 0, then it would just be at 1. So, okay, questions? Okay, so if the car is located at the point x equals 0 at t equals 0, okay, so this is now telling us where the car started. We want to find the values for the position at each point listed on the table to the left. Okay? Oh, do I really mean this? Do I want you to do all of those points? Because some of these are going to be hard to do. Like that first one. I think we can do it. Alright, 0, position is 0. It tells us that, right? At t equals 0, position is 0. So, if we are looking at 1, I got this little tiny triangle. It's going to be 1/2 times the base, which is 1, times the height, which would have to be 1/2. So that'd give us 1/4. At 2, now my triangle has a base of 2 and a height of 1, so I'll get an area of 1 there. right here, I'd have a triangle. It's going to be 1/2 times my height is going to be 3/2, and my base would be 3. So that is going to give me 9/4. And then here, now my base is 4, my height is 2, so that'll give me a area of 4. Are we okay there? So we're just looking, this would be our area at first, then we're looking at those first 2 sections together, the first 3 sections, and now the first 4 sections. Here, we got 2 more blocks that are being added, so that'll be 6. Here, we got 2 more blocks that are being added, so that would be 8. And then here, this from 6 to 7, that should have an area of 1, because we do 1/2 times 2 times 1, so that would get us to 9, right there. Okay, what's going to happen at this point? After 7, what's going to start happening to our position? We're going to take away from it. So this area right here, I'm going to use red because it's negative, right? So it has an area of 1, but it's going to be negative, so that would get us back down to 8. And then whenever I add in this section right here, that has an area of 3, so I would subtract 3 more, which would give us 5. And then I'm going to add on here. It would only let me make my table so long. And then we got 4 units right here, so that would, we subtract 4 more, and that would give us 1. And so this gives you like the exact position at those different points, right? If we start at 0. What would happen to these numbers if I change that where instead of starting at 0, we started at 10? So what would all these numbers, what would happen to them if we started at 10 instead of starting at 0? What? So basically, like, if I start at 10, so this is a theoretical, this is not this question. If I start at 10, that means this right here would be 10, right? So the amount, the area under the curve would still be the same right there. It'd still be 1/4. But I started at 10. So my position would be 10 plus 1/4, right? So I'd have 10.25 there. And then I'd have 11. So basically you just add 10 to all of these numbers that we see here, right? Here I would have 12.25. Here I have 14, 16, 18, 19, 18, 15, 11, right? So this would be if x equals 10 at our original position, right? So wherever that starting point is, we would still have that change would be positive. So when it's positive, you're adding. When it's negative, you're taking away. But you're just starting at 10 instead of starting at 0. Does that make sense? All right. So the fundamental theorem of calculus. So we talked about one version of the fundamental theorem of calculus. Okay. The fundamental theorem of calculus tells us that if we looked at the one version that was this. If we take the derivative of the integral from a to x of f of t dt, right? It was just going to give us f of x. No plus c. Putting things in there that don't go there. It just gives us f of x, right? So the fundamental theorem of calculus recognizes that the derivative and the inverse are inverses of each other. So this applied to definite integrals. So definite integrals are ones where we're going to have a capital A, A to B. Both of these are constants right here. So we're looking at going from 1 to 4, or 0 to 3, or 7 to 10, right? So if f is continuous on the interval from A to B, and capital F is the antiderivative of f. So that antiderivative means that it would be if we integrate that function, right? If we use those rules that we were learning where we increase the exponent by 1 and divide by that new exponent. So if we have, like, our capital F is our function here, lowercase f is the derivative of that capital F. So if we are integrating a function, then the capital F of B minus the capital F of A is going to give us this value. Let's think about this in terms of velocity and position, okay? Because I think that helps, okay? So velocity, if we integrate velocity from 1 to 4, okay? So let's just, we've worked some with velocity. V of t here is our function. If we take the derivative of v of t, what does that give us? That gives us acceleration, right? That'll give us the rate of change of the velocity, which is our acceleration. That's not the direction we're going here. If we integrate v of t dt, what does that give us? Position, right? So position, right? And this, of course, is velocity. And this is acceleration. So I think it really helps to think about this in terms of velocity, position, and acceleration to kind of understand why this works. So if we integrate velocity, so it's like we're going, I like to think of it as like going up or down steps right here. We're at velocity, we're going up a function, that gets us to position, right? Integrating gets us up. So that would give us position. So that would give us x of t. And then the way that we're going to denote this sometimes is we're going to put this bar right here, and we still put our limits here from 1 to 4. So what this means is the change in position from t equals 1 to t equals 4, right? Because that area under the curve gives us the change in whatever function we're dealing with here, particularly in this case it's position. So if I want to know how much my position changed, I just need to know where I started and where I ended, and I subtract the two, right? So if I know that I started at 10 and I ended up at 20, well, let's say I started at 10 and ended up at 35. What's my change in position? It'll be 25, right? Just 35 minus 10 there. So it's just, we're taking where you end up and subtracting where you start. So that will just be x of 4 minus x of 1, right? So that means you would just take position at t equals 4 and subtract position at t equals 1. You always want it in this order, the top minus the bottom for that whenever you're integrating. And so that would give you your total position. Of course, I'm just dealing with like, I'm just dealing with a generic problem here we don't have an equation for, so we can't actually figure that out here. So if I have acceleration, and I'm integrating that from 0 to 3, when I integrate acceleration, what do I get? I get velocity, right? So this is going to give me v of t from 0 to 3. So what I'm looking at here is the change in velocity from t equals 0 to t equals 3. And if I want to know the change in velocity from t equals 0 to t equals 3, I just need to take my velocity at 3 and subtract my velocity at 0. So integrating just takes you like up a notch on the equations, and then you're just subtracting the end point minus this, or you're doing end point minus the starting point. All right, so let's look at this. This is calculator active, so grab your calculator for this. So today, we are not, well, we might actually need to do this on the calculator, I guess. Let me see. Okay, so f is a differentiable function. F of 3 is 2.345. It gives us the equation for f prime. Then it asks us for f of 5. Okay? Do we have the function f? Okay? Can we come up with it? Do we have like an easy way of coming up with the formula for that? For natural log of x squared plus 1. We've not done any rules for that yet, right? If I was teaching this as normal, you wouldn't have any rules for any of it yet, because I usually don't teach you the rule where you like increase the exponent and divide out front. So you won't be using those rules on these. But I do know if I integrated f prime of x from 3 to 5, right? When I integrate f prime, what do I get? I would get, I'm going to write this intermediate step, but you don't have to. I would get f of x, and then I would need to find that difference between 3 and 5, right? So that means my integral from 3 to 5 of f prime of x, I should put dx right here, is going to be f of 5 minus f of 3. Now, you're going to have to use your calculator on this. So, let me show you guys how to integrate on the calculator. The calculator will do these integrals for you. So, when you have something that you don't know the rules for, the calculator can do it. So, I prefer to put it in Y1. You don't have to. I'll show you how to do it both ways. So I'm going to put f prime in Y1. So I've got natural log of x to the second plus 1. So if we put this into Y1, now that's our equation for f prime there. We want to go back to the main screen, and we want to integrate that function from 3 to 5. To do that on the calculator, you're going to hit F3. You're going to choose number 2, integrate. And we're going to tell it y1 of x, because we put that into y1. We have to tell it comma x. And then you can enter your limits of integration here. We're going to put comma 3, comma 5. And I'm going to hit the green button before I hit enter, because I would rather have a decimal here. So the calculator will tell me what I get there, 5.63144. So this value right here, using the calculator, is 5.63144. Right. You can also do this without using the y1. You would just integrate, and you would just tell it natural log of x squared plus 1 comma x comma 3 comma 5, and it'll give you the same thing there. So if you don't like using y1, you don't have to. I just prefer it because it makes it easier to type in this part here, but it's up to you. So you get that. So this value is 5.63144. I don't know f of 5, but I do know f of 3. They told me that it was 2.345 there. And so I could just add that 2.345 over here to this side, and that should give you D for your f of 5. Okay, let me offer you another way of thinking about this as well, okay? Because I feel like there is another, it's essentially going to do the same thing, but there's another way of thinking about this that is also helpful. When I integrate from 3 to 5 of f prime of x, right? That is f of x evaluated from 3 to 5. This is the change in f from 3 to 5, right? It tells me how much change. So like whenever we're thinking about that first problem with the car, whenever we got 9, whenever we integrated from 0 to 7, that told us that the position changed 9 feet, right? It went 9 feet to the right. So this gives me the change. This is where it was at 3, right? So at 3, I was at 2.345, right? That's like my starting position, right? So if I want to know f of 5, I could take the starting position, f of 3, and I could add my integral from 3 to 5 of f prime of x dx, and that will give me my value of f of 5. So it's like starting position plus the change is going to give us the ending position there. So if you did that, it would be 2.345 plus this 5.63144, and that is also going to give you that same number. It's just really like a rearrangement of doing it the other way for that. But it may be more helpful to think about this, particularly on some problems that we'll be looking at. Okay, questions? Okay. Selected values of the twice differentiable function f and its derivative f prime are given in the table. What is the value of the integral of f prime from 0 to 3? Okay, so when we integrate, whenever we integrate f prime, what do we get? F. And so if we evaluate f from 0 to 3, that means we'll be doing f of 3 minus f of 0. Can we find those values? Yes, they are on our table, right? So f of 3 would be 10, and f of 0 would be 4. 10 minus 4 would give us 6. So C would be our answer. These table problems make it way easier, don't they? Yeah. Okay, questions? Okay, so this time, g is the differentiable function, and we know g of 4 is 0.325. We got g prime, and this time we want to know the value of g of 1. So we're going to do this a couple ways again. All right, so I know they give me g of 4. They're asking me about g of 1. So what I can do is I can use those as my limits of integration. If I integrate from 1 to 4 of g prime of x dx. When I integrate g prime, it gives me g that I'm going to evaluate from 1 to 4, which is going to be my integral from 1 to 4 of g prime of x dx is going to be g of 4 minus g of 1. And so this, definitely we got to use the calculator for that. We do not know how to integrate that, nor will we ever know how to integrate that by hand. Or at least not under my instruction. If there's a way, I'm not aware of it. So we're going to type this in. I prefer y equals, so that's what I'm going to use. I like to see what I've typed in to make sure it looks right before I integrate. And I don't like having 57 parentheses in one entry. So everybody got typed into y1. Alright, so the calculator, we're just going to go back to the main screen. We're going to integrate. We're going to tell it y1 of x, comma, 1, comma, 4, and I probably should have hit the green button before I hit enter. Surely it's going to do a decimal. I might have broken it. No, I did it. So we're getting 0.21552. We know g of 4 was 0.325 minus g of 1. And so now you just have a simple equation to solve. You're going to subtract that 0.325. And so that gives you negative 0.109428. That equals negative g of 1. And then so that's going to give you 0.109428 is your g of 1. And that is A there. Okay. All right. So, I do want you to think about this in a different way. So, I want you to think about this a little differently, kind of like we did the other, okay? So, another way to think about this is the starting point they have given me is g of 4, right? So, I know my position at g of 4. So, if I want to know g of 1, I could take g of 4, and I want to know, in this case I'm kind of going backwards, right? So I'm going back to 1. So if I want to write an integral here, how would I write this so it would give me g of 1? Okay, I could add the integral not from 1 to 4. You would have to do 4 back to 1 of g prime of x dx. Or, the other way to think about that is you could subtract the integral from 1 to 4 of g prime of x dx. Because, see, this part right here, the integral from 1 to 4, if we have it in order, tells me change from 1 to 4, right? Our change in f of x from 1 to 4. So if I'm starting at 4, I need to go backwards from that. So I have to subtract that change because I'm going back to 1 instead of adding that to it. Or I can do the integral backwards, which will give me change from 4 to 1. And if you do it that way, you can add. So if you do that, if you take that g of 4, which is 0.325, and you subtract the integral from of y1 of x, comma, x from 1 to 4, you should see we get that same answer. There, hopefully, if it'll do it. I think it can do it, maybe. So it'll give us that same answer. There, so, but because you're starting at the furthest right, you got to subtract because you're going backwards for that. So, let me think about this for a second. I don't think there was assignment. We may have to go. We may start on tomorrow's. After this, let's see. Because I'm pretty sure y'all can do those 3 problems pretty quick. Let me see. All right, let's see. Was there something else we were supposed to do with this? I can't remember. Let's go away. There we go. No, this one doesn't have an assignment other than these 3 problems. So I want you to do these 3 problems right now. And then we may begin just a little bit of tomorrow's because tomorrow's is not going to take a terribly long amount of time either. It would be, oh, I forgot to tell you, we're going to do FRQ quiz for this week because it's a short week. We're going to do it Monday for 2 reasons. We could do it Thursday, but that's a pretty short turnaround. And 6.9 takes a little while to do. It's not very fast notes, so I don't want to do an FRQ quiz on that day and try to get those notes in. So we're going to do the FRQ quiz on Monday next week instead of trying to get it in this week. So assignments due Monday, yes. Do I have it set as due Monday? Let me see. Yes, I think that's it for that. All right, so try these 3 problems and then we're going to go over those.